All right. Well, good evening, students. My name is Mr. Rich. I appreciate you joining me here tonight for our Sunday night 8 p.m. Mr. Rich Q&A. And what I want to do today is I want to start off our session by going over my top 5 math tools. Most of these are going to be online math tools, but I've got a few at the very end that might surprise you that aren't really online tools, but things that you want to be able to utilize to be successful at math. So the very first thing that I'm going to talk about tonight in terms of the tools that I recommend for success in math. First one is Desmos. If you've ever tutored with me, you know that Desmos is something that I use all the time as a calculator and as a graphing tool to try to show you concepts. And so just a few things that you may know about Desmos, or maybe you don't know, is that we use Desmos usually online. We go to desmos.com and we go to the graphing calculator part of Desmos. But Desmos also has a feature, or actually, I should say, has an app for your phone or your iPad or any of your devices that you can load and utilize there. So a lot of students, when I'm teaching math in high school, I've had students load it onto their iPhone so they could use it. It's got the same functionality as you do online. So it's an awesome thing. I recommend that you get it on all of your devices. A few other things that I wanted to mention about Desmos. If you have been preparing for the SAT, you know that the new digital platform for College Board that they use to administer the SAT test, a calculator embedded in it, and it is the Desmos calculator. So if you know how to use Desmos online, when you go to the SAT, then you're going to be able to use that to its full advantage to help you on the test. There's another thing that I wanted to mention to you that you may not know, and that is that when you go to Desmos, you can create an account. And so you can save the graphs that you may generate in your account so that when you log in some other time, you can pull those up. I'm going to show you an example of that here in just a minute. So I highly recommend that you do go to desmos.com, create an account for yourself. And what I want to do tonight, real briefly, since I got other things I want to cover, I'm just going to show you some of the things that you can use for to help you be successful in math. So we're just going to kind of scratch the surface here and look at those. I'm going to switch over to take a look at Desmos. So let me get that set up here and I'll share my screen back. There we go. So I'm in Desmos right now. And I mentioned to you that when you log in as yourself, that you can save graphs. So I've saved a few here. The cool thing is that there's, if you didn't know, when you click on the upper left, but what I wanted to show you a few things that you can use Desmos as just a straight up calculator, even if you wanted to add fractions. Look at this. I put in here 4/5 plus 1/3. And when I hit enter here, it gives me the answer of 1.13 repeating. Well, if I want to convert it to a fraction, if I hit this button up here, this little fraction button, it shows me that it's 17/15. So you can just do some straight up mathematics on Desmos. Now, the other thing that you can do with Desmos is you can graph to find intercepts, right? If I have the function f of x equals 2x plus 3, and I click that button right there to turn it on, there is the graph. And you can zoom in and out with the scroll on your mouse. So, and if I zoom in on this, I can find out what the y-intercept is. And notice Desmos knows what points you might be interested in on the graph. And so it's not hard at all to find that the y-intercept there of 0, 3. Coming over here, there is the x-intercept at negative 1.50. I graphed here a quadratic, and I've just turned it on. I don't see it, but if I scroll and zoom out a bit, I can see the parabola right there. And the vertex, if you know anything about the vertex form of a parabola, we should expect that vertex to be at 4, -4. And sure enough, there it is. Notice it does show me the x-intercepts right here, and there is the y-intercept. If I wanted to solve a system of equations, suppose that my system of equations was this straight line and this quadratic. If I graph them both at the same time, I can find their intersection points very easily. So you can see that 9, 21 is a solution to the system, just as well as 1 comma 5 is also another solution to that system of a linear equation and a quadratic equation. So you can use it for that. If you ever use the TI-84 and its graphing features, you can really appreciate how easy it is to find these intersection points. On the TI-84, graphing can be a real challenge, but of course, if that's all that you have during a test, that's all that you have, and you want to know how to use the TI-84. But as you're trying to learn math concepts and connect graphs to functions, Desmos, you can't beat it. Now, those of you that are my calculus students, it will graph derivatives. Now, most of you that are in calculus, you haven't gotten yet to the derivatives unit, so this may not make a whole lot of sense to you. But if I have a function and I want to graph its derivative and I turn this on, what I've told Desmos to do is to graph the derivative of my g of x function. And it turns out that this straight line is the derivative function for g of x. So just want those of you that are in calculus to keep that in mind, that you definitely can use this with calculus. It does have calculus features. A few other things that I wanted to point out. I think I'm just going to show you one other thing, and that is that you can use sliders on this where you have letters that represent not a variable, but possible constants or coefficients that you may put into the equation. So for example, I've created this function here called j of x. And notice the variable is x, but I've included, I'm going to put a square in here. I meant this to be a quadratic. And so this, you probably recognize this as being the vertex form of a quadratic, where a would be a constant and the h and the k would be actual numbers that I would plug in there. Well, if I turn this on, if I turn the actual graph on, there's the parabola. Now, what is it graphing? It's graphing where a, h, and k are all the number 1. Now, I'm going to change h to be 0, and I'm going to change k to be 0, like that, and a to be 1. So what it's graphing is your parabola that has a vertex at 0, 0. Well, if you know anything about the vertex form of a parabola, of a quadratic, that h right there, when you change it, it's going to move the graph over to the right or left. So I've just moved the slider to make h3. So what it's graphing is 1 times x minus 3 to the second power plus 0. K is a 0. So by changing h to be 3 so that it's graphing x minus 3, it has shifted the graph over 3 units to the right. Also, if I change this k to be a positive number, notice that it is going ahead and moving the graph upwards, because we know that's what happens when we tack on a constant at the end of a function. It causes a vertical shift up or down. The a, the coefficient that's in front, that's going to be a vertical stretch. So if I make that a to be greater than 1, then you can see that it's vertically pulling it up, making it rise faster. So those are some features right there. Also, and I'm just scratching the surface here of what you can do with Desmos. Let me go back to the presentation here. So that's my number 1 thing. Be familiar with Desmos. Get it loaded onto your phone and your iPad. The second thing, the second math tool that I think that you want to use is a TI-84 calculator. Those of you that are in Algebra 2, you're not required to be using a TI-84. In fact, your teacher will tell you most likely that you can't use one on the summative exams. But still, if you plan on going into higher levels of math, into pre-calculus and maybe beyond into calculus, you might as well get the TI-84 now and start learning how to use it. Because once you learn how to use the TI-84, it's something really that you don't want to go back to a regular calculator. The one thing that I think you would appreciate right away is that the TI-84 knows the order of operations. So you can pull up a TI-84 and enter in a mathematical expression. And I'll pull my TI-84 up here so you can take a look at it. When you enter in an expression from left to right, it knows the order of operations. It knows PEMDAS. So for example, if I say 3 times 9 minus 2 plus 6 minus 9 times 2 and hit enter, I can be assured that that 16 is following the order of operations. It knows to do the multiplication first, right? It's going to do the 3 times 9 is 27, and the 9 times 2 is 18, and it'll do the addition and subtraction from left to right. So that's one of the great things there. All right, I have a student trying to get in. All right, let me see. So bear with me. I'm going to try to help a student get connected here. So that's the TI-84. I'm not going to go into it much more of it here, but you can enter in functions and use function notation. So it's very, very, very powerful. And maybe in a future Mr. Rich Q&A, I can go into some of that. So that's tip number 2, right? The TI-84 would be the second math tool that I definitely would recommend that you use. Third one that probably most of you haven't heard of, it's called the website wolframalpha.com. And it also has an associated app that you can load onto your devices, whether it be the Google Play Store or the Apple. Okay, trying to help a student here. There we go. Now, what does Wolfram Alpha do? It's one of those websites where you can ask it to solve an equation for you. And it's especially useful to those of you that are in AP Calculus. And it will show the steps that you would have to use to solve an equation. That's one of the things that I really like about it. Now, the thing is that if you're using the free web version on your computer, it won't show you the complete steps to solving a problem. But if you do go onto your iPhone or your iPad and you buy that version of it, and I think there's a fee for purchasing the Wolfram Alpha app on your iPhone. It was, if I remember right, it was less than $10. But you can actually click a button and it'll show you how to solve an equation. And this is not something that you want to use to try to cheat on homework. So, hey, I don't want to do the work, so let me just plug it in here and have it spit answers out. No, this is a tool that you use so that you can try to understand the steps in solving a problem if you get stuck. I'll show you what the website looks like. So let's pull this up. So here was Desmos. Now I'm going to move over to Wolfram Alpha. This is it. There's not much to it. It's almost like I call it the geeks Google. You can actually type in a question or a problem with straight up text. So for example, if I wanted to factor a quadratic, I could use the word factor and say, hey, factor x squared minus 3x minus 18 and hit enter. All right, and it gives me the result. So it did the factoring there for me, which is great. But if you wanted to see the step-by-step solution, if I click on that, it says Go Pro now. So you would have to actually look at it, you would have to purchase the app. And I'm not sure if that may be a monthly subscription, but the nice thing is when I loaded it on my phone and I bought it probably 7 or 8 years ago, I paid the one-time fee and now I have it active on my phone and I can use it. And those of you that are taking calculus, you can definitely use it to learn how to do derivatives, how to do integrals. If you're taking AP stats, it's also good for doing statistical work. So it's a great thing. And maybe I'll do down the road, I'll show you some of the features that you could, that Wolfram Alpha has. But for now, I just wanted to show it to you and make you aware of it. I'm going to go back, and that was my number 3. Right. So number 1 was Desmos, was my top tool that you want to incorporate into your math learning. Second one is highly recommend getting a TI-84 calculator. Third one was the Wolfram Alpha website. Number 4 was the PhET simulator, PhET, and there's the website, phet.colorado.edu. It gives you visual simulations for a variety of math and science topics. It's great for some teachers have used it for like doing virtual science labs. It's really pretty cool, physics labs and such. It's also good if you're taking statistics, if you're in AP stats or probability stats. It's got some good simulations to help you understand the concepts of maybe what standard deviation is mean and median, linear regression, all of that, those kinds of things you'll find in PhET. And I'm not going to go over to the website, but it's something definitely for you to check out. The fifth thing is one that I'm sure that most of you have used at some point, Khan Academy. And you can create an account there and access practice problems for any math class that you might be taking. And it'll actually take you step by step through the concepts, give you practice problems, the associated videos that go with them. And they also have an SAT prep program there. So it's just one of those things that's been around for many, many years and is always a top resource for you to use. All right, some bonus resources beyond that. These are the ones here that I think you really need to consider. If you're in a math class and things are pretty tough, or you're expecting things to be tough, you need to connect with your friends. Maybe create a text study group so that if you're working on homeworks, getting ready for a test, you can communicate with some other people who might be able to help you. And that is so important. If I'm going into a class, if I was a high school math student, I'd want to find like the top 5 smartest people and be their friends, find out how I could connect with them through text if I needed some help, and see if I could make connections that way. So that's definitely a resource for you. Another one is your teachers, obviously, but don't forget that sometimes you could go to a teacher other than the teacher who's teaching you the course that you're taking. Suppose that you're in Algebra 2 and you want to get the input, maybe a different perspective on how to work a problem. Go to one of the other Algebra 2 teachers right before school or after school, and they'd be, I'm sure, most of the time happy to help you. And also, I would say this too: don't be afraid to ask teachers of other topics. Right? I was a math teacher for years in Duval County, and a lot of the students knew that I was an engineer, and they would come to me and ask me about physics problems. They would ask me chemistry, which usually I didn't know the answers to those, but I knew a little bit of chemistry. So you can go out and reach out to other teachers who might be able to help you on your concept. Like, for example, you could go to a physics teacher and get help on algebra for sure. So if you had a good relationship with a physics teacher, then maybe that's something that you can do. If it's someone who's teaching statistics, sure, they're going to know algebra, probably pre-calculus, and they could help you as well. So that's just a tip there. And always, getting different perspectives on the same topic from multiple teachers or your friends or YouTube videos. Those are all good ways for you to really master the concepts that you're studying. So anyways, those are my top resources that I would recommend. And what I was going to do, it's about 22 minutes after the hour now. So what I was going to do for the rest of this session was I'm going to go through algebra, pre-calculus, and calculus. And about where most of you are at in those classes, I'm going to work a few problems that you might find helpful. So I'm going to first start off with Algebra 2. Most of you in Algebra 2 are either looking at or you're getting ready to solve absolute value equations. So I'm going to do an easy, a medium, and a hard absolute value equation problem. And let me give you first the concept when you're solving absolute value equations. The very first thing that you are doing when you're solving absolute value equations is you are going to isolate the absolute value portion. Whatever is inside the absolute value bars, you need to get that on one side of the equation by itself. Once you do that, once you've isolated that by doing algebra on both sides of the equation, then you're going to split into two separate equations. Well, we'll call it split into two cases. So the problem really is going to become two problems. And what you're going to do is you're going to set one of the problems where the right-hand side of the equation is going to be the positive value, and the other one is going to be where it becomes the negative value. Let me just show you how that's going to work. So here's an easy problem. I'm trying to find the solutions to this equation. The absolute value portion is already isolated. So I'm going to split it now into my two cases. Here are the two cases. X minus 9 is 5. So I drop the absolute value bars, create that equation. The other case is going to be x minus 9 equals negative 5. So that's what I'm doing. I'm changing the sign, making it negative, and then I'm going to solve those two independently. So I'm going to add 9 to both sides. I get x equals 14. Add 9 on both sides. I get x equals 4. Those are my two solutions to that. Let's go to the medium difficulty problem. This isn't much more difficult. It's just that I do need to remember to isolate the absolute value portion. So I'm going to subtract 17 before I split into the two cases. So when I subtract 17 from both sides, I'm going to get a 6 over there. Now we go to the two cases. Case number 1, y equals 6. Case number 2, y minus 1 equals negative 6. Add 1, we get a 7. Add 1, we get a negative 5. And really, you want to check your work too when you're done, because I'll show you on the next problem what happens if you don't check your work. It's possible on absolute value, at least on more complicated ones, it's possible to get what we call extraneous solutions, solutions that really aren't solutions because they don't solve the equation in reality. But here, when you try 7, right, you get 7 minus 1, which is 6. Absolute value is 6. 6 plus 17 gives me 23. It checks. But also negative 5 works because negative 5 minus 1 is negative 6. And when you take its absolute value, it gives you the positive 6. 6 plus 17 gives you the 23. Okay, next, let's go to the hard one. Now, on this one, what I have to do is I do have to isolate the absolute value portion. So I am going to add 5n to both sides. So the first step is the absolute value of 8 minus 2n. When I add 5n to both sides, I'm going to get 6n plus 2. I am now going to break it up into the two different cases. Over here, I drop the absolute value and then just write down the right-hand side as it is. And then I'm going to solve that for n. I'm going to move the n's to the right-hand side. So this is going to make this 8n. I'm going to subtract 2, which will give me 6. So it looks like n is equal to 6/8 or 3/4. Now let's go do the other case here. The other case is going to be where the right-hand side here is going to be negated. So it's going to be 8 minus 2n. And I'm going to negate the 6n plus 2. So I put a minus in front of it. That means that this is going to become 8 minus 2n equals negative 6n minus 2. Now we'll bring the negative 6n over here to make this 4n. The 8's going to come over and become, looks like that's going to become a negative 10. And so I get n equals a negative 5/2, like that. Now the question becomes, are both of these valid solutions to the original equation? Well, let's start with the 3/4. Right? If you stick the 3/4 back in for n on the, let's use this, right, on the left-hand side here, that's going to give me 8 minus 2 times 3/4. And that has to be equal to 6 times 3/4 plus 2. And let's see how that works. So this is going to be 8 minus 3/2, right? That would be 6/4 or 3/2. This is going to be 4 goes into 6. Let's see, so that'd be 3/2, so that'd be 9/2, it looks like. It'd be 3/2 times 3 plus 2. This, let's keep going with this. So this is going to end up being here, 8 minus 1.5, that's going to give me 6.5. Let's convert that to decimal. That is 4.5 plus 2, going to give me 6.5. So it checks. Now, cutting it, let's do this a little bit shorter. This one is not going to work when I stick in a negative 5/2. And here's how I know that that's not going to work. Because if I put negative 5/2 in here for 6, that means that on the right-hand side of this equation, I'm going to have a negative number, right? Because 6 times negative 5 over 2, that's going to be negative 15 plus 2 is negative 13. There's no way to take the absolute value on the left-hand side and get a negative number. So this is what we call an extraneous solution. And so we would discard it. And our only answer then becomes n is equal to 3/4. Let's move on to onto Precalc. And I'm going to do another easy, medium, hard on this. And here we're dealing with polynomials. This comes out of lesson 1.4, 1.5 of AP Pre-Calculus. Let's take a look at this one. I think I did this with a few students tonight that I was working with. This gives you a polynomial function, and it wants to know the intervals for which the function is less than 0. Well, the thing about polynomials is that if I want to know where the polynomial is going to be up or negative, in this case, I need to know where it's going to be negative. I need to know where the function is going to be 0. So I do need to find the zeros of this function. Let's see if I can get my pen to work here. There we go. So I need to set the equation equal to 0. So I'm setting my f of x equal to 0. Well, the good thing about this problem is it's already in factored form. It's a polynomial that's been factored. So I can set each of the factors equal to 0. So the zeros end up being 0. When I set 2x equal to 0, I get x equals 0. When I set the next factor equal to 0, I get a negative 1. And when I set that factor equal to 0, I get 3, like that. Right? Don't forget, if I were to take x minus 3 over 2 as a factor and set it equal to 0, multiplying both sides by 2, I get x minus 3 equals 0. Therefore, x equals 3. So those are my 3 zeros. Now, here's how I'm going to evaluate this. There's really 2 ways to do it. I'm going to make myself an x-axis. And these are the values where this polynomial is going to cross the x-axis. I know it's going to cross the x-axis and not bounce because for each of these factors, they have what we call a multiplicity of 1. Each factor has an exponent of 1 on it. It's going to cross at negative 1. It's going to cross at 0. And it's going to cross at x equals 3. The other thing that I know about this polynomial is I know that it is a third degree polynomial. In other words, the highest power on the variable is a 3. If I were to multiply the polynomial all the way out, my highest degreed term, it would be 2x to the third, because there's a 2x times x gives me 2x squared. When I multiply it by the x over here, it's going to give me a positive 2x to the third. Maybe it may end up being a 1x to the third because of this divide by 2 here. But the point is, it's a positive leading coefficient with an odd degree. That tells me that functions that have odd powers, odd degrees, with a positive leading coefficient, that means that their end behavior is up to the right and down to the left. So this function, this polynomial, has to go and turn, cut through the 0, turn, cut through the 3, and then head up to infinity that way. And now I can assess where the function, over what x values, it is going to be less than 0, below the x-axis. All of these values over here, this is where the function is negative, and here's where the function is negative. That's the interval of x values right there that solves that. Now, I mentioned there was another way to do it. If you didn't know the end behaviors like I did, which is pretty fast, if I know the end behaviors and I know it's going to cross the x-axis there, well, if I didn't know that, one of the options you have is to select what we would call a test point for each of the intervals that are created by the x-intercepts. So just to the left of -1, I could say I have x equals -2. Here I could say, well, I'll use x equals a -1/2. And here I'll use x equals 1. Here I use x equals 4. Now, what do I do with these 4 test points? Well, they're points that are going to represent all the points that are in the interval. So what I'm going to do is I'm going to take the original factored version of this polynomial and ask myself, when x is -2, what would I get in terms of positive or negative right here? Well, if x is -2, that factor will be negative. Obviously, it's going to be a -4, but I really don't care what the number is. I just want to know positive or negative. When I stick a -2 into this one, it's going to also be negative, because it'd be -2 plus 1. So it's a negative times a negative. And then when I put -2 here, -2 minus 3 is -5. It's also negative. Well, what do you get when you multiply negative times negative times negative? That results in a negative answer. So that's how I know that my y values have to be negative in that interval. to the left of -1. Well, if I move over to using x equals a -1/2, and I go back, that's going to be a negative. But look what changes with this factor, x plus 1. When x is only a -1/2, that factor is now going to be positive because it's -1/2 plus 1. So that would be a negative times a positive. And then with a -1/2, that's still going to be negative. But the result of a negative times a positive times a negative turns out to be positive. And sure enough, the function does go above the x-axis and is positive. And you can do the same for x equals 1 and x equals 4 and 2. You'll get a negative followed by a positive when you stick those test points back into the factored form of the polynomial. That was the easy one. Okay, let's go to the medium problem. I think this might have been a little bit easier than the last one. This gives us a graph of function f, and it says that the absolute extrema, the relative extrema, and the point of inflection are labeled. Let A, B, C, D, and E represent the x coordinates at those points. Which of the following intervals is the graph of f increasing and concave down? Well, one of the things that you're learning in this first unit of AP Precalc is that concavity changes for polynomials, or it can change. And in this case, you can pretty well recognize that in this region, the function is concave up. And in this region, it sure looks like it's concave down. So that means that if a polynomial changes concavity, or it's different concavity in different sections, there must be, it would stand to reason, a specific point at which that concavity changes. And that does happen at a point called the point of inflection. So in this case, this point C is the place where it switches, where the polynomial switches from being concave up to concave down. Now, I think you all would recognize that this stretch right here that I'm marking in red, that's where the function's increasing. But that red streak where it's increasing really is split into two separate sections, because here, during the upper red part, that's where it's concave down and increasing. And over here, this is where it would be concave up and increasing. This question is asking us, over which of the following intervals is the graph increasing and concave down? Well, there's only one region where it's increasing, and I've marked it in red. And the only place that it's concave down, excuse me, is after point C. So it's really from C to D that it's both increasing and concave down. Let's move to the hard one. This question says, in the XY, that's supposed to be XY plane, I would imagine. In the XY place, the graph of a rational function f has a horizontal asymptote at y equals -1 and a vertical asymptote at x equals 3. Which of the following could be an expression for this function called f of x? Well, I'm going to start with the process of elimination here. I'm going to try to find some of these answers that do not have a vertical asymptote at x equals 3. Well, the one that sticks out the most that does not have the vertical asymptote at x equals 3 is question B. Right? We know that a vertical asymptote will come about when you have a 0 in the denominator that does not get canceled by an identical factor in the numerator. There is an x minus 3 that would have created a vertical asymptote at 3, except that it got removed by the x minus 3 in the numerator. So that means there is a vertical asymptote at x equals 1, but not at x equals 3. So I can remove this as a possible answer. No vertical asymptote at x equals 3. This one does for sure have a vertical asymptote at x equals 3 because of the x minus 3 factor in the denominator that does not get canceled. So that one's still alive. Over here, there is an x minus 3. When you first glance, you say, well, it doesn't really get canceled by any factor in the numerator. But actually, it does, because I can rewrite that numerator by pulling out a negative out of this, and that would become x minus 3, x minus 2, and this is x minus 3 times x plus 1. So it turns out, in fact, there's a hole at x equals 3, because the x minus 3 on the bottom gets canceled by the x minus 3. So no vertical asymptote here. All right. And this one also, by the same logic and factoring out that minus that I did up here, this does have a vertical asymptote right there at x equals 3. So now we have to turn our attention to the other criteria, and that was we have to have a horizontal asymptote at y equals -1. So my remaining two answers, remember, to determine horizontal asymptotes, we're going to look at the highest degree terms on both the top and the bottom. So my highest degree term here on the top is x squared. My highest degree term on the bottom, if I were to expand that polynomial at the bottom, that would be a -x squared. And when I have the same degree top and bottom, that means that the horizontal asymptote will be at the ratio of their two coefficients. So that means that I think I like answer C, because it looks like y equals -1 is a horizontal asymptote. Let's just confirm that we don't have that for question D. My highest degree term right here would be x to the second. Highest degree term on the bottom, if I were to expand that polynomial, would be x to the second. It has a horizontal asymptote, but it's at y equals 1. So C is my answer. That is the pre-calc. And if you've got any questions for next week, you can send them to me at askmrrich@gmail.com, or you can come here and you can post them in the chat, and I'd be happy to answer them. So those of you that are here, I think I have a few students here. If you have any questions about your class, go ahead and post them over in the chat, and I'll be happy to try to answer them. I'm going to try to go to calculus. And my calculus students are learning limits. And I'm going to do an easy, a medium, and a hard. So here is a multiple choice question that tells us to find values of C such that g of x would be continuous everywhere in its domain. Well, when I look at g of x, it's a piecewise function, and it looks like it's some quadratic when I'm to the left of 2. And when I'm to the right of 2, it looks like it's a linear function. And they want me to find the value of C that will make it continuous everywhere. Well, one thing I know, quadratics, linear functions, they are continuous everywhere. So the only place I could possibly have a discontinuity is where the two functions are going to meet up at x equals 2. So what we know is this. There's a much faster way, I guess, to do this without going through the explanation I'm about to give you, but I want to go over the idea here. One of the things that we use limits for is we use them to define continuity of a function. So we can say this, that a function f of x is going to be continuous at a certain value of x that we will call a. So I'm just going to pick some value at which the function's continuous if the following is true. First of all, what has to be true is the limit as x approaches a must exist. That means then if you're checking for continuity, that's a two-sided limit that I just wrote there, x approaching a. So you have to check from both the right side and the left side to see if the limit does exist. If it does exist, what must be true for continuity is that whatever that limit is, it must be the same as f of a, like that. And that's the definition of continuity, because you can, if the limit does exist, that means that from the left side and from the right side, the functions are getting really close and they're going to meet at the same y value, but you need to plug the hole with a dot, okay? And this would ensure, if this is true, that means that I am going to have a solid dot right in the hole where the two functions are coming together for the limit to exist. Anyways, that's the idea here. So what I'm going to do is I am going to show that, or I'm going to determine what C would be by doing this. I'm going to plug 2 in for x in both of these and set them equal to each other, because I want the limit to exist from both the left and right hand side. Remember, for that to be true, we have to check both the left hand limit and the right hand limit. They must be the same value. And so for this function to be continuous, I'm doing the left and right hand and evaluating the limit by direct substitution. So here's what I'm going to do. I'm going to plug 2 in for x. So it becomes 2 squared plus c squared. And I'm going to set that equal to this expression with 2 plugged in for x. So this becomes 5c minus 2. And now I'm going to solve for c. And it looks like we're going to end up with a quadratic. So I've got 4 plus c squared equals 5c minus 2. So sure enough, this is a quadratic. So I'm going to get all of the terms over on the left-hand side. So we'll do c squared minus 5c plus 6 equals 0. We'll solve this by factoring. We're looking at our answer choices. We can keep our eye over there. I'm kind of liking, well, there's lots of 2's and 3's there. So let's finish the problem out. So we'll factor this by saying that this is going to be c minus 3, c minus 2. And therefore, c could be a 3 or c could be a 2. I'm liking answer A. I'm going to check my work and make sure that if c is a 2, which would make, if c was 2, it would make g of x, x squared plus 4, and it would make this 10 negative x. So let's see. If I plug 2 in for x, I get 8 right here. And if I plug 2 in for x, sure enough, I get 8. So that would be that this would mean that the function has to be continuous right there. Right, the fact that this is or equal to 2 ensures that the hole is going to be plugged, right? That's going to happen because of the fact that it's greater than or equal to 2. If we let c be 3, then the g of x function becomes x squared plus 9, and this would become 15 minus x. And then when x is 2, I get 13. When x is 2, I get 13. So it's going to be continuous whether c is 2 or 3. Let's evaluate a limit. The very first thing that we do when we evaluate a limit is we try direct substitution. So what happens here is when we plug 0 in for x, we get 0 plus sine 0 over 0. Well, sine of 0 is 0 from the unit circle. So we really get 0 over 0. Teachers probably told you that when you try direct substitution and you get 0 over 0, that's what we call an indeterminate form. And we really don't know what the answer is. I'm going to erase this because it means that I have to do some sort of algebra simplification, or I could use some graphical technique to try to evaluate what this limit is. But let's assume this is non-calculator active. Got to figure out how to do this with algebra. Well, one of the things that you have learned, hopefully you've learned about limits, is there is a special limit involving sine. And it's this limit. The limit as x approaches 0 of sine x over x. That limit exists, and the answer is 1. Now, at the very beginning of this hour, I was showing you Desmos, right? If you wanted to like make sense as to why is that limit 1, that doesn't even make any sense. How is that limit as x approaches 0 equal to 1? Well, let's go take a look. We've got a little bit of time. So I'm going to jump over to Desmos, and I'm going to graph that function. So let's get rid of all of these. And let's graph the function sine x over x. There it is. I want to be in radians mode, so I'm going to click this wrench right here. I am in radians mode. Now, I need to zoom in on this a bit. And I'm going to rescale this so that we get a better look at just what this function looks like. So let's do that. And then let's adjust the y here to go from -2 to 2. Okay, that looks better. And I'll zoom out just a bit. So anyways, that's the behavior of the function sine x over x. We're talking about what does the value of this function get close to the closer we get to 0. So let's zoom in right here where x is 0. What happens is from the right-hand side, you can see we're getting very close to 1. In fact, when I land right on top of that coordinate, Desmos tells me the function is not even defined at x equals 0. In fact, there's a hole right there. That's what this tells us. The function does not exist at x equals 0. However, when we come in from the right-hand side and in from the left-hand side, the closer we get to 0 from both sides, the closer we get to 1. So the limit does exist. It's 1. Well, let's go back to the problem that we're trying to solve. What I'm going to do is I'm going to use this result to evaluate this limit. And here's how I'm going to do it. I'm going to split this into two separate fractions. I'm going to simplify this as x over x plus sine x over x. Because there's one denominator of x, I can do this. This is something we can do with fractions, split multiple terms in the top into separate fractions with the same denominator. Now, why would I do that? Or why does that benefit me? So I'm taking the limit now of this. Well, the other thing that you've learned about limits is there are what we call properties of limits. And that is that I can split limits by addition and subtraction into separate limits if it suits my purposes. Well, and by the way, x over x is 1. So let's go ahead and simplify that. That's just the number 1. So really, my next step is to say that the limit as x approaches 0 of 1 plus the limit as x approaches 0 of sine x over x. Well, this thing I know. That thing is the number 1. So I'm just basically replacing or substituting 1 for that. And then I need to know what this limit is. That limit is 1. Right? The function 1 is a horizontal line at y equals 1. So everywhere the limit does exist, and the answer would be the number 1. So my answer here ends up being 1 plus 1. The limit is 2. All right, let's move on to the hard one here. This one does cause students some grief when they get into their first test. This is asking what is the limit as x approaches 2 from the right-hand side of 2. Well, we are going to try direct substitution and see what happens. Well, when we substitute 2, and I am going to get 0 in the denominator, but I want to know whether I'm going to get 0 in the numerator. Okay. Now I can already look at that numerator and know I'm not going to get 0 because I'm going to get, these are all going to be positives. So what am I going to get? I'm going to get 12 plus 14, it looks like, plus 2. I get a 28 over 0. Now, that doesn't mean undefined, right? Most of the time in math, when you try to divide something by 0, we just say, oh, it's undefined. But we got to stop and understand, we're not talking about what is this value. We're talking about what's the limit of this function as x gets close to 2. Now, here's the other thing that we know. If I got a 28 on the top and a 0 on the bottom, that means that there is a vertical asymptote at x equals 2, right? Now, how would I know that? Well, it looks like when I factor, if I were to take this function and write it in its factored form, I'm not going to say it's equal to, I'm just talking about, let's factor this. I get that. Now, does this factor? I'm not sure that that factors. Maybe it does. Let's see. It does. That would be 6x. Yeah. So it does factor. But so this is x plus 2. Now, this tells me that there is a hole at x equals negative 2, but a vertical asymptote at x equals 2. Now, that means then if you know that you are dealing with a right-handed or left-handed, what we call a one-sided limit at the place where there is a vertical asymptote, your answer is going to be infinity or negative infinity. And your job is to find out which one it's going to be. If it was a two-sided limit, okay, let me just answer this question. If it was a two-sided limit and there's a vertical asymptote, there's no question. The answer is does not exist, right? The limit will not exist. The two-sided limit will not exist at a place where there is a vertical asymptote or where the function, at a vertical asymptote. But it is a one-sided limit from the right-hand side. Here's how I'm going to evaluate this. I'm going to go back and rewrite this limit as x approaches 2 from the right. Let's write it in its factored form. I think we said 3x plus 1, x plus 2. Difference of squares, x plus 2, x minus 2. So we can remove that. X plus 2 cancels. What I'm going to do to determine whether this, at this asymptote, at this vertical asymptote, whether the function is going up to infinity or down to negative infinity, is I'm going to choose a number just to the right of 1 because it's coming in from the right at 2. So I'm going to say, what if x was 2.1? What would I get right here? Well, we've already canceled the x plus 2's, but if it's a 2.1, that's going to be a positive on the top and 2.1 minus 2 is still going to be positive. My answer is positive. Therefore, my answer here is positive infinity. If I came in from the left, if we changed this problem, we said, well, yeah, but what's happening at the vertical asymptote when we come in from the left side? Well, it would have changed my answer because I would have picked a number just to the left of 2, 1.9. Well, with x equals 1.9, that numerator is still positive. But now when I put 1.9 into x minus 2, that's going to be a negative number. And therefore, it would be a negative infinity. So one thing I know that this function's doing over here at 2 is from the right-hand side, it's going up to infinity. And then from the left-hand side, it's going down to negative infinity. All right, so we're just about out of time. And that is the 3 problems that I was going to work for calculus. Okay, so thank you for coming, students. And next week, we'll do it again at 8 p.m. So send me your questions in advance to askmrrich@gmail.com, or come here and you can post them in the chat and I'll be sure to answer your questions. Okay, everybody, have a great week and I'll see you next week.